Okay, everybody, we're gonna start now. Hello and welcome to the second session for reinforcement learning introduction. And I think we're gonna start right away. So today we're gonna talk a lot about Q learning. So the previous day we did a little bit of background, did not cover everything. So the Q learning was really planned for the last session. So we didn't get to there, so I'm gonna talk about this a bit today. And we're gonna talk. Once we got Q learning done, we're gonna talk about deep Q learning, and this 2 sessions gonna be like majority of the class, and then we're gonna talk about Rainbow, and we're gonna talk a bit like all the small improvements that were done in Rainbow all the way. And the one point we're leaving out because of time is the distribution of reinforcement learning. So you either can look it up yourself, or if you're interested, we can talk about this in the next session. So last session we talked about the dynamic programming and a little bit about the Monte Carlo approach. And the Monte Carlo approach was like you just take the game or the model or the environment and you keep running it. You play the episodes, and then you kind of average your data over all the runs you do. It's kind of the Monte Carlo approach. Like in Monte Carlo, you just keep running simulations, and then you take the average of all your simulations. And the dynamic programming approach, we don't really play the game. We just go through all possible states, and each time we iteratively update our value functions for those states. And the power of Q learning is also, the way it is called is like temporal difference learning, but the algorithm is called Q learning. So we're gonna refer it from here on as Q learning.
Could you repeat that 1 minute, because I distracted a student? The premise of Q learning, the difference. Could you repeat that, please? I distracted a student.
So it's called temporal difference, and this is just a way to call Q learning. So temporal difference is more the concept, and Q learning is the algorithm. And temporal difference, so TD stands for temporal difference. We want to estimate the value function, and say in Monte Carlo, we have some kind of estimate. And we have some kind of better evaluation of the estimate, and we say, okay, our next estimate is we just update it. So it's what we also did with the greedy one. So this is like taking an average over a sequence, all right? You want to average, and then you take a new sample, you want to add the sample to your average. And here we just did it over 1 divided by n for the greedy one, but in Monte Carlo you have some kind of learning rate. In dynamic programming, we just try to estimate giving the value function of a state, giving the state, and we want to estimate the expected return. And what does the TD function does? It combines those 2 elements together. So what you say is, we have our estimate, right? Our current estimate. And we update our current estimate. We play the game, we do 1 action. And then we have our current estimate where we are right now. We play 1 step. So we know, okay, what was the reward in that step? And we say, okay, what was so you know a better estimate of that system, right? Which was kind of the estimate of the next steps plus the current reward we get times the future discount. So we say, okay, this is the reward we get, and this is like the better estimate of we get. We take the difference of those 2. And then with step size alpha, we just update our current estimate.
So what does TD stand for?
Temporal difference. So you can think of this as a TD error. So what is this? So
isn't it the advantage function?
No, something else. So this is our current estimate, right? And this is a little bit better estimate of the current estimate. So we say the current estimate, we say, this is the value function of ST. But the value function ST is nothing than the current reward plus all the future expected reward. So say I want to value how good I am, estimated, and you have absolutely no knowledge. You have some function that just approximates it. And then you can play a game. So you get this reward as additional information, right? And this additional information helps you to update, to get a better estimate of the actual value of the current state. So we say, okay, the current estimate minus the expected estimate is some kind of temporal difference error. And we say our current estimate, if you go back, our current estimate is basically our current estimate or improvement, or stepwise improvement is our current estimate plus step size times the error rate. So we kind of move always in the direction of the error. We kind of iteratively always slightly improve our expectation of the value. So is there any questions for this?
Yes.
Yes.
Because when you're looking at TD, it's essentially just going to be a stepwise as opposed to the entire episode being played out. What I was really trying to understand is, like, say for instance, if we're initial state is A and we're moving to state B, right? So how does the estimate of state A improve by looking at state B? That concept I couldn't understand. Because if you look at this, it just says that the current estimate of A, say for example, is 30. So essentially I'm saying that V of ST is equal to 30 plus minus that is also going to become 30. Say the reward is 5. And the next state, the value is going to be, say, 50.
So the value function is kind of related to the reward again, but it's not exactly the reward. So the way the value function is defined, this is just how it defines, is like reward plus gamma of future rewards for the whole end of the episode. And what you can do is, like in the Monte Carlo, I just sample over. I look how many times I was in the state, and then I just average my expected, like all this future expected rewards. So I calculate the rewards, all the future rewards, and I weight it with like this kind of discount, future discount. And then I get the value function. And then, I've been in this state 10,000 times, so I just take the average of those 10,000 times.
So effectively, B, ST plus 1 is calculated using Monte Carlo, is that it?
No. This is how Monte Carlo does, right? Okay. And here, we just do it stepwise each time. Okay. So this is also an imperfect estimation, right? And this is just how the value function is defined. So my expected value of a state is basically the reward of my current state plus the discounted future of all possible future states. And then we say, okay, we don't have a good estimate of this, right? But just how this value function is defined, has to be a better estimate of the real value than this. Because I draw the reward, and it gives you additional information on it. And it allows you to create a generative list. And then the difference between these two is kind of the error rate, right? And then you just you improve your estimate a little bit. Each time you go through this state. And this is not one state, but rather like you have your state, right? And then you do your action, right? If you do some kind of epsilon greedy, like it's based on your policy as well, how you update, right? So you say, okay, for my best possible action, this is like my future estimate of this B as t plus 1.
Can you repeat what's the output of value function?
So we have a state value function and a state action value function. So the state value function.
And this is state value function,
this is
right?
State value function. So the state value function just returns the value, like the value of the state. So you have to think about this, like how favorable is the state? Is it a favorable or a disfavorable state?
So silly question. What's the difference between reward and the value I get from the value function?
So the reward is direct reward. It's immediately. You do an action, you get your reward directly. The value function kind of estimates how good your state is. So you have to think about your reward is the direct, immediately one, and the value function is like you want to plan ahead, you want to think ahead, you want to see, okay, this is a good state, this is a favorable state I want to be in, and these are disfavorable states. So I don't want to move to these disfavorable states, I want to move myself in these favorable states. Of course, a favorable state is a state where I have more expected future rewards.
And how does that relate to action value?
So if you do the state function, then your input is just the state. But if you have a action and state, then it's basically your expected return given a fixed action, right? Here, this is basically different ways to determine this, but most of the time it's going to be like a greedy way. So we just say, okay, the best possible action will give me the value function of the next state. But if I say static action value, then the input is like both state and action.
Is the output of value state function a vector of all?
No, it's one single value.
Mm-hmm.
Yes.
I'm just saying that from a practical purpose, when you're really looking at building different models, out of all of this, I guess a couple of things that you'll be really able to control, or sort of can think of as hyperparameters, would be the alpha and the gamma. So from a practical purpose, how do we use the alpha to train our models? Like, what's the intuition that we should generally follow for that?
The alpha is a learning rate.
Just the step size, for instance.
Yeah, it's a learning rate. So some small value, like 0.001, 0.00001.
So effectively, what are we trying to do by putting alpha onto it? What exactly?
It's like the whole, for neural networks, you have like a step size. And if you select your step size too large, you're just walking too big steps, you cannot find the global optimum. And if you select it too small, it will just take you a very long time to find the optimum, right? So it's step
It's like
size.
supervised learning.
It's a learning rate.
Yeah, and
Yeah,
the new information is like it's basically R plus gamma, whatever. It's like a new piece of information comes and you train your weights based on that kind of.
All right, any questions?
Could you quickly elaborate on the differences between your V functions on top and at the bottom? On top, you have a value function that looks at st plus 1 minus the value. Is there a missing bracket?
This is the part of the bracket.
Yeah, it's just zoom in, basically.
Let's just zoom in.
Right. So then there is a missing bracket. The closing bracket after v st plus 1.
No, it's here.
At top.
Right. At top, it's missing.
Oh yeah, here. Yes.
Okay.
You're right.
Okay. Question resolved. So it's the same thing. Okay.
So what's the advantage if you do it this way, right? Say you don't need to require the model of the environment. Like you don't need for dynamic programming. We knew from one state what are the all possible next states, right? And then the action of the next possible state. You don't really need to know the whole environment for dynamic, unlike dynamic programming. And in Monte Carlo, what you do, you play the whole game, right? And you play it over and over and over and over again and take an average. The disadvantage is, first of all, you have to wait for the episode to finish, so you can take your average in. And for Monte Carlo, it's like very hard to estimate the state action value function because you're also like you have some kind of policy and you randomly run through, so you're kind of bound by the policy where you go, what you see. And the thing is that both TD and Monte Carlo, they converge to optimal policy over time. So you can take a good look at this.
Sorry, this one was to identify the value function of a policy or to identify the best policy?
So it is the same, more or less. So if you have the Q-learning, you just determine the optimal value function or the optimal value function for all state actions or for most state of actions. And then you also have the optimal policy. So
basically, if you have like the value function optimal, then like if you do greedy policy, you have the optimal policy.
But you only have the state, right?
Sorry?
With the state, you won't have the action, right? Because if you look at the value of the state, you won't have the value of action.
So
Well, the reward comes from the action you take.
Q-learning or Q-table stores all value action pairs. So you have the value action one, and you kind of, this is just a general idea how it works, right? The algorithms I showed.
I think also like another benefit of Q-learning is that if you go to the same state in the middle, you already have the updated value of that state. Basically, you learn more rather than the other one. Which,
for Monte Carlo, the problem is that first you have to wait until you finish.
and if you cross the
And
same,
also, the other problem is if you get a very big reward at the end, it's going to be very difficult for you to understand if this action, how much did this action contribute for you getting this big reward at the end. And this is what we're told. You have like a point, the yellow dot is the agent, and it just randomly plays through the game at the beginning, because each time you visit a state, it just updates the value function of the state. And then kind of like, if you take a greedy of all the values and state action values, you kind of get like a fixed policy, right? You take a greedy algorithm for what I mentioned, and then this arrow is just the greedy, like just which action results in the next value, highest value function. Where you can think of it like you are here, right? You have to actually go left, you go right, and you see the value functions of the next state, right? So you just say I go this direction, like then it's this direction. So it's the maximum greedy of all your possible next states. And then you, of course, so you think of dynamic programs a bit of like a trade-off, right? So you see these states, they're more likely to occur, so we're frequent to visit those, and you get better estimates of the value of the states. These states, you're less likely to visit, and then they're kind of still more random, like no matter how many times you train. Especially once you found the optimal policy, your TD algorithm will just follow the optimal policy over and over and over again.
Sorry, the goal here was to go from the first square to...
So each of these fields has like a reward.
Right.
So these, they have no rewards, like 0. And these have like negative rewards. So these red ones have negative reward. And this field has a positive reward.
Yeah, I'm just trying to figure out why did it sort of build that wall in front of the positive reward?
The gradient.
You do it yourself. You can like toggle whatever you want. Like I can change, you see, I can do like this. Somewhere you can change the reward of the cell. When I say, okay, I increase this, and then you can toggle it, and then it will just upgrade, right? And everything gets positive because this gives so much points. And you can say, okay, I give this minus 130. Now there's no way to make like a good score, so it just randomly walks all over the place.
Question.
Yes.
So if you have a dynamic environment, like it's changing, is it multiplayer problem?
Well, depends. Depends. There are also dynamic environments that are not multiplayer.
Okay. So
like there is also, if you want to say I want to do multi-agent machine reinforcement learning, and how you define multi-agent, right? Are they collaborative? Are there like multiple agents, but all the agents are controlled by one, like AI, by one player? Or is it like multi-agent and it's like competitive, right? So it's not.
And the game theory comes in, right? If it's competitive, game theory comes in.
Yeah.
And then it's a zero sum, whatever, right?
Yeah, it all depends, right? It's like you cannot generalize all these things. Any other questions?